Hello guys, and welcome back to the reaction zone. In today's lesson, we're going to look at how to use the quantum numbers to determine the orbitals that are present in a particular energy level. The question on the board is as follows. Determine the number of orbitals present when n is equal to 3. As a reminder, let us recall that an orbital is determined by 3 quantum numbers: the principal quantum number, the azimuthal quantum number, and the magnetic quantum number. So let's get right into the solution to this problem. Already, the question has given us the principal quantum number, which is n is equal to 3. Now, the azimuthal quantum number, the values of the azimuthal quantum number depend on the principal quantum number. And the values of the azimuthal quantum number ranges from 0 to n minus 1. So this therefore means that when n is equal to 3, L will be equal to 0, 1, 3 minus 1. Then n will be equal to 0, 1, 2. So let's start with n is equal to 0. When L is equal to 0, the magnetic quantum number ML is going to be minus 0, 0 plus 0, which is still equal to 0. Now let us recall that the magnetic quantum number, the values of the magnetic quantum number depend on the azimuthal quantum number and ranges from minus L to 0 2 plus L. Also, when L is equal to 1, let's not forget, L has 3 values, 0, 1, and 2. So when L is equal to 1, the values of the magnetic quantum number M will be minus 1, 0, plus 1. And when L is equal to 2, the values of ML will be minus 2, minus 1, 0, plus 1, and plus 2. Now that we have this, we can now determine the set of quantum numbers for each of the orbitals that are present. So, let us begin to list them. The first one is n is equal to 3. When n is equal to 3, the first value of L is 0. So that will be n is equal to 0. When n is equal to 0, the only value of ML is also 0. ML is equal to 0. This will be the first set of quantum numbers for the first orbital. The next one is n is equal to 3. L is equal to 1. When L is equal to 1, there are 3 values of ML, minus 1, 0, and plus 1. We'll take the first one. ML is equal to minus 1. When N is equal to 3, L is equal to 1, the next value of ML is equal to 0. When N is equal to 3, L is equal to 1, the next value of ML is equal to plus 1. Now we can move on to the values of L is equal to 2. When N is equal to 3 and L is equal to 2, the first value of ML is minus 2. So ML will be minus 2. When N is equal to 3, L is equal to 2, the next value of ML is minus 1. So ML will be equal to minus 1. When n is equal to 3, L is equal to 2, the next value of ML is 0. ML is equal to 0. When n is equal to 3, L is equal to 2, the next value of ML is plus 1. ML is plus 1. When n is equal to 3, L is equal to 2, the next value of ML is plus 2. So each of these sets of quantum numbers determines an orbital. And let's not forget that the particular quantum number that tells us the type of orbital is the azimuthal quantum number. So the values of the azimuthal quantum number would let us know whether an orbital is an s orbital, or a p orbital, a d orbital, or an f orbital. So for the first set of quantum numbers, the value of n is 0, so that is the 3s orbital. For the next one, the value of n is 1. N is equal to 1, the orbital is a p orbital. So this is a 3p orbital. For the next one, n is still equal to 1, so this is a 3p orbital. Next one, n is still equal to 1, this is also a 3p orbital. Next one, n is equal to 2. When n is equal to 2, when n is equal to 2, the orbital is a d orbital. So this is 3d. N is equal to 2, so this is also a 3d orbital. N is equal to 2 here is also 3d. N is equal to 2 here, which is also a 3d orbital. N is equal to 2 here, this is also a 3d orbital. When we look at this set of quantum numbers from here down to this place, we will discover that for this, as well as this one here, this 3, we'll discover that their values of the azimuthal quantum numbers are the same, but the values of the magnetic quantum numbers are different. The same thing, if we look at this one, this one, as well as this, their values of the azimuthal quantum number is the same, but the values of the magnetic quantum numbers are different. Now let's start with this 3 here. The magnetic quantum number determines the orientation of orbitals of a particular subshell in space. For the first one, where n is equal to -1, it is the 3px. For the second one, where mn is equal to 0, it is a 3py. For the third one, where mn is equal to +1, it is a 3pz. So that tells you that these p orbitals here are oriented in space in different directions. Now, for the next 5, their principal quantum numbers and orbital quantum numbers are the same, their magnetic quantum numbers are different. For the first one, where mn is equal to 2, this is the dxy orbital. For the next one, where mn is equal to -1, this is the dyz orbital. For the next one, where mn is equal to 0, this is the dz squared orbital. For the next one, where mn is equal to +1, this is the dxz orbital. And for the final one, where mn is equal to +2, this is the dx squared y squared orbital. Now, if we look at these ones, these 3 here, we will discover that their principal quantum number as well as their orbital quantum number, that's the azimuthal quantum numbers, are the same, but their magnetic quantum numbers are different. That tells you that the p orbital is degenerate, and it is threefold degenerate. That is why you have 3 p orbitals that have equal energy, because a degenerate orbital or degenerate orbitals are orbitals that have equal energy. So what this means is that the 3px here is equal to the 3py and is also equal to the 3pz in terms of energy. When we look at the d orbitals, we also discover that the d orbitals here have the same values of principal quantum numbers as well as azimuthal quantum numbers. That tells you that these d orbitals here have have equal energy as well. They are also degenerate. So the d orbitals are also degenerate orbitals as well. However, unlike the p orbitals, the d orbitals are five-fold degenerate, meaning that there are 5 d orbitals that have equal energy, in contrast to 3 p orbitals that have equal energy. So this is that the 3dxy orbital is equal to the 3dyz orbital is equal to the 3dz squared equal to the 3dxz, which is equal to the 3dx squared y squared. So please note, p orbital is threefold degenerate, meaning that there are 3 p orbitals that have equal energy. D orbital is five-fold degenerate, meaning that there are 5 d orbitals that have equal energy. So to answer the question, the number of orbitals present when n is equal to 3, you count the orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the number of orbitals present and the principal quantum number n is equal to 3 is 9 orbitals. Thank you very much for viewing, and see you in the next lesson.